Good morning, ladies and gentlemen. My name is Artur Gańcza. I'm from the Gdańsk University of Technology, and together with Professor Maciej Niedźwiecki, I am the author of a paper describing the optimal regularization in the identification of non-stationary systems. Such systems appear in different applications in underwater acoustic communication. One of them is self-interference cancellation in full duplex underwater acoustic communication. In full duplex communication, both communication devices can send and receive information simultaneously using the same bandwidth. As a consequence, the received signal from the far-end transmitter is contaminated by the signal from the near-end transmitter. The self-interference is formed by the transmitted signal that reaches the receiver directly and by its reflections from the bottom, the water surface, and nearby objects. The movement of these natural reflectors is a source of non-stationarity of the system. This is why the recorded signal can be modeled as a mixture of the known transmitted signal convolved with the time-varying impulse response of the self-interference channel and the signal from the far-end antenna contaminated with the site-specific noise. To remove the self-interference, one should find reliable estimates of system parameters based on the available input and output signals and use them to subtract the estimated self-interference signal from the output signal. The figure depicts typical trajectories of a simulated underwater channel. One of the well-recognized methods for the identification of non-stationary systems is the local basis function method. It starts from the assumption that locally, inside some analysis window, parameter trajectories can be described as linear combinations of known functions of time, called basis functions. This allows one to use, inside the analysis window, a higher order but time-invariant model. The estimation problem can be solved using the weighted least squares method. Although the estimates of basis function coefficients describe the system inside the entire analysis window, they are used to find parameter estimates corresponding only to the current time instant. Then the analysis window is shifted by one sampling interval and the estimation procedure is repeated. It is straightforward to check that when parameter trajectories belong to the subspace spanned by the basis functions, then the LBF estimates are approximately unbiased. However, unbiasedness is not the most important thing. Our ultimate goal is to minimize the mean squared estimation error, which can be decomposed into bias and variance components. So in fact, we are looking for some bias-variance trade-off that will minimize the MSE score. This can be achieved with a properly designed regularization. A perfect example of such an effect is visible in this figure. The red line shows the true impulse response of a time-varying system at one particular time instant t, and the black line depicts the LBF estimates or regularized LBF estimates. As you can see, with the proper regularization, we were able to substantially reduce the variance of the last 25 taps at the cost of a slight mismatch of the first 15 taps. Overall MSE score for this system dropped. We want to apply regularization to the vector of system parameters. So, in order to apply this technique with the LBF method, we need to change the regularization matrix so it could be applied to the vector of basis function coefficients. This results in a formulation of regularized local basis function method. Now the question remains, how to choose the regularization matrix? It turns out that under some assumptions, the optimal regularization matrix in terms of the MSE can be found. The assumptions listed here are in fact not very restrictive. The first assumption is typically met in telecommunication applications. Regarding the last assumption, if the covariance matrix of system parameters remains unknown, one can use its estimate obtained, for example, based on parameter estimates from the LBF method. Under these assumptions, one can derive the following formula for the optimal regularization matrix. Note that the noise variance is typically unknown, but can be replaced by its estimate obtained using the LBF method. It might happen that the covariance matrix of system parameters will also vary with time. In such a case, we propose an adaptive algorithm for choosing the regularization matrix. In this approach, one runs several algorithms, each one with a different regularization matrix, and for each one of them, one computes the local sum of squared leave one out interpolation errors. Next, at each time instant, one chooses this algorithm for which this local sum is the smallest. Note that the same adaptive scheme can be used to choose the number of basis functions and the length of the analysis window. It is important to note that these errors can be obtained without computing new estimates of parameter trajectories. One only needs to modify the interpolation errors obtained from the regularized LBF scheme using the scaling factor beta. Note that the inverse of matrix S might not be a byproduct of computing regularized estimates. So one can replace the beta factor with its simplified and computationally cheaper version. We compare the LBF method with its regularized version using simulated underwater communication signals. Time-varying parameters were generated as low-pass filtered complex Gaussian noises. The input signal was a circular white binary, and the noise was circular white Gaussian. The power profile of system parameters was decaying exponentially to reflect the power absorption loss typical for acoustic telecommunication. To evaluate our methods, we use the fit score, averaged over time, and different realizations of parameter trajectories. The fit score allows one to measure similarity between the true and estimated impulse response at each time instant. So a score of 100 corresponds to a perfect match. We used also a cosinusoidal window to put more emphasis on data closer to the center of the analysis window. In our experiment, we compared the LBF method with the RLBF with different regularization matrices, corresponding to different choices of the constant gamma. We also show results obtained for adaptive algorithms with the exact and simplified calculations of the scaling factor beta. Finally, we checked the results for the two-step algorithm, in which we use the LBF estimates to estimate the covariance matrix, and based on this, we perform regularization. As you can see, each of the regularization methods provides improvement of the fit score compared with the score obtained for the LBF method, despite the fact that none of the regularization matrices is exactly equal to the optimal regularization matrix. It is also important to note that the improvement that we obtained was consistent and visible for every realization of parameter trajectories. To summarize, the problem of identification of a non-stationary stochastic system was considered and solved using the time-localized variant of the regularized basis function approach. The proposed regularization can substantially improve LBF performance. The regularization matrix can be chosen in an adaptive fashion, and the proposed adaptive procedure yields results that are comparable with the results provided by the best algorithms incorporated in the parallel scheme. Thank you for your attention.